Welcome back, everybody. Another exciting video in the Blue Glow Electronics Tube Amp 101 lecture series that I'm doing. This is episode 5, focused on parallel and series resistance circuits. If you'll remember, last time in episode 4 we went on a deep dive into resistance and what it was all about. This video I'm going to get a little more practical, tell you how to put these resistors in circuits and how to do some calculations around them using Ohm's law that we've learned about. But I do want to throw out a disclaimer about this video, and that is that there are hundreds of videos already on YouTube that teach you how to calculate parallel and series resistance in circuits. So I'm just going to scratch the surface here, not go too deep, just enough to give you the concepts. You can go watch lots of other videos to get deeper in the subject matter, but then come back, because what I'm really wanting to teach you in this video is help you understand how these parallel and series resistance circuits actually get used in tube amplifiers. And I'll give you some real good examples of that, so that as you learn how to calculate these things, you can bring it back and apply it to tube amps, and you can say, well, I know why that's there in that schematic, and I know what it's actually doing. That's my goal in this video. So hang tight and we're going to dive into it. All right, let's talk about a circuit. A couple basic schematic symbols I'm going to introduce you to here, if you don't already know them. But first off, a schematic is basically a graphical representation on paper, or it could be digital, of an actual circuit. And so it's how we visualize electronics. It's one of the hardest parts about electronics, is you can't actually look inside of an amplifier and see anything happening. You can't see current flowing, you can't see voltage drops or whatnot. So what we try to do is draw these things up on paper and graphically represent them in ways that people can understand. So the first little symbol here is just really simple. Hey, we got wire, it's just a line. Next is an energy source, which in this case is a battery, and we draw that with a symbol with a long line, a little shorter line, a little bit longer, another long line, and a short line. And if you draw it or not, it's implied that the plus is up here. The positive end of the battery is where the first long line is. So sometimes you'll see that drawn, sometimes you won't. This is actually a switch, which is nothing more than a line that has the opportunity to either be open in this case, or you could actually take that part and close it, like in this case, which would allow electricity to flow through. This would not allow electricity to flow through. And our last little symbol down here is just a symbol I've drawn for a light bulb, a little circle here with a filament inside of it. And this is actually nothing more than our load in this case. All right, what a circuit actually is anytime you have an energy source, okay, and in our case a battery, and you connect it to a load, right, of some sort, through a series of wires that complete the circuit. And in this case, it does not complete the circuit, because this switch here is open and does not allow a current to flow through. So in this case, we have what is called an open circuit. In other words, it's a circuit that has the potential of completing and closing the loop, but because we have a break in the signal here, we actually have what's called an open circuit. As soon as we come along and kind of close this switch right here, then we have what's called a closed circuit, and electrons could then flow through here back into the battery to complete the circuit. So in that case, as soon as we would close this switch, then this light bulb would start emitting light at that point, because the filament inside of this light bulb would have current flowing through it. It has some resistance, and the resistance inside of this in a light bulb is designed, instead of putting off heat, to put off light. So as the current flows around through here, remember the old Ohm's law that we did last time? There would be a voltage. This thing has some resistance to it. So if we knew the voltage here and we knew the amount of resistance here, we could use our handy dandy I is equal to V over R, right? And we could calculate what this amount of current flowing through this circuit is. And because it has some resistance right here, and if we knew the current, we could also calculate, remember, I is equal to, V is equal to I times R. Then we could calculate the amount of voltage drop across this resistor, or in other words, the difference in potential between this point right here and this point right here in this circuit. So back in 1845, this German physicist named Gustav Kirchhoff, it's Kirchhoff, Kirchhoff. He was doing some experimentation with various circuits or whatnot, and he basically came forward with a couple principles that have stuck since then. And the first one we're going to call KVL, otherwise Kirchhoff's voltage law. It's very important to know, and it applies immensely to everything we do in electronics. And basically what this Kirchhoff's voltage law says is that the sum of all of the voltages in a circuit basically is equal to 0. In other words, the voltage being put out by this circuit going around and being consumed and coming back must be equal to 0. So if this is like a positive 12 volts, then in this case this light bulb would use 12 volts up. So if it's using it, we could consider it a negative. And so if you add those up, when you get back here, you end up with 0 volts. And it's a pretty simple concept, but what it's really saying is kind of the conservation of energy law, and that is that there cannot be any more energy consumed in a circuit, right, than what is provided into the circuit. And likewise, the energy provided into a circuit has to be consumed by the circuit when connected. So it's pretty simple here because you got one load device, but you'll see here in a little bit we'll have more than one load device, and you'll start to understand how that voltage gets divided up across those devices. So that's what KVL is all about. Kind of the sum of what gets put into the circuit is what gets used by the circuit. No more, no less. If you put 6 volts into a circuit and somehow you had a device that used 12 volts, well, somehow you have created energy in your circuit which breaks all laws of physics. It's impossible for it to happen. And so that's why we have this law basically. All right, so up next, what we will call a series circuit is when you have an energy source, some type of closed loop like we've got here, and there's only one path for the electricity to flow. In other words, this is the path for the electricity to flow from one end of the battery to the other. Similarly here, one path all the way around. Similarly here, one path all the way around. And the difference between these three drawings is this drawing here basically has one load or one resistor. This one has 2 and this one has 4. A couple things for you to learn as we go forward that'll be fundamental is that in a series circuit like this, the math for adding up how much resistance is there is really simple. So let's just say we had 12 volts right here, and right here we had 12 ohms, right? Our little ohm symbol and 12 volts. How much resistance is in this circuit? Well, it's really easy. It's 12 ohms, right? Well, let's say we have 12 volts on this one, and we have 12 ohms of resistance here, and we have 12 ohms of resistance here. How much resistance is in this circuit? Well, I haven't told you that, but our total of a circuit is equal to R1 plus R2 plus R3 plus R ... however many circuits happen to be, how many resistors happen to be in that circuit. So in this case, it would be 12 plus 12, R would equal to 24. Well, in this case, if we had, a 12, a 12, a 12, and a 12, right? We would have 12 and 12, what, 24, 36. We would have 48 ohms of resistance in this circuit. So it's really just a matter of adding all these resistances up. Okay, another little circuit here, no different than the one we had before. So here we have a 12 volt source. We have a 8 ohm resistor as R1, and we have another resistor here, R2, of 4 ohms. Well, if you'll remember, R total equals to 8 R1 plus 4 equals to 12 ohms, right? Let me show you another way that you could represent this circuit. It's called an equivalent circuit, and we use this theory a lot when it comes to electronics. Let's pretend that we had the ability to kind of draw a little imaginary line right here, right? And if you're this battery and you're looking this way into the circuit, maybe you can't see all the things that are happening on down here. Maybe there's 20 resistors here, right? But you really don't care, because what you really have at this point looking in this direction is R total that you're seeing from the battery. So in this case, we could actually redraw this circuit if we wanted to look like this, where this would be R total, or in our case here, this would be 12 ohms of load. So in other words, this battery, when looking this way, is going to see 8 ohms plus 4 ohms equals to 12 ohms of load, and we could redraw this circuit to look like this. It's called an equivalent circuit when you do that. In other words, you're kind of shortening everything from this point over and summarizing it here as R total. It's a concept we'll use throughout electronics as we move on into this amp, especially as we start talking about, maybe the load that a tube may see, a preamp tube may see based on, what's on beyond it in the amplifier stage or whatnot, if that makes sense. All right, now we're moving to the other type of circuit that exists, and that is a parallel circuit. And what happens in a parallel circuit is you basically have more than one load. In this case, we're using resistors for our load. And these loads are in parallel with each other. In other words, there's it's a bad resistor drawing. We've got two loads here that are in parallel with each other, and they've been connected in some way, shape, or form. And then we've come over here and connected a battery to them, basically. So, back to old Kirchhoff, right? Here comes KCL. Guess what KCL is? Kirchhoff's current law. And what it basically said is, let's see this little point right here. There's another little point right here. This is where we have basically a branch off. In other words, current's flowing along, and then it comes to a point where it says, hey, I've got two different paths I could take, right? I could go forward here, or I could turn and go this direction. And so we'll call this little point right here a node and a schematic. And what Kirchhoff's law basically says is when you enter a node, whatever enters the node, so going into the node, equals the sum of what leaves the node. And similar to that law of conservation of energy, nothing can be created or lost in a node. In other words, if there is 5 amps of current entering a node, there must be 5 amps of current leaving the node. So maybe 3 amps go one way, 2 amps go the other, or it could be that 4 amps leaves one node and 1 amp leaves the other, but no energy can be gained or lost in the splitting of a circuit at a node. So if you've got 5 amps in, 5 amps have to come out of that node. And that's basically what KCL stands for. So this is where it gets a little more complicated at this point. You know, this being R1, this being R2, right? You might have to use your calculator on some of this, but R total, the way it works out is it is 1 divided by 1 over R1 plus 1 over R2 plus 1 over R dot dot dot. Could be 3, 4, 5, 6, 7, 8, 9, 10, whatever. So let's learn a couple basic things here. Let's just say R1 is 12 ohms and R2 is 12 ohms. So in this case, and you know, it's not as simple to be honest. So 1 over 12 plus 1 over 12. Does that make sense to you? 1 over R1, which is 12, plus 1 over R1, this is 12. This ends up being 1 over 0.083 if you do the math, plus 0.083 ends up equaling to 1 over 0.166. And I did a little bit of rounding here, but then you divide 1 by that number, and guess what you get? You get a total of 6 here. So it's a pretty easy one here if you get used to working with parallel circuits. But if you have a parallel circuit with 2 resistors that are equal, the R total here will kind of equal to half of these resistances, which makes sense. You've got an amount of resistance here, and current's going to flow down through here. But since this resistor is equal, an equal amount is going to flow through here. And since the resistance here was 12 and the amount here was 12, the total resistance this thing would see is 6 ohms. But if you can't figure that out, you can always do the math or just jump online. There's lots of calculators for this stuff that'll help you kind of figure out from, you know, just type in your resistor values and it'll come back and it'll tell you exactly how much the total resistance is at that point in time. You know, it's not quite as easy when, you know, you've got, you know, if this was a 12 ohm resistor and this was a 6 ohm resistor, you'd have to go through the math to figure that part of it out, if that makes sense. All right, let's apply some of Kirchhoff's voltage and current laws to just a couple different circuits here. First one here, really simple circuit. And if you remember Kirchhoff's voltage law, let's just say we have 12 volts here, a battery. Well, guess what? There's 12 volts sitting right here, right? And the implied is here there's 0 volts sitting at this point. So there's a 12 volt potential, right, across these 2 points, this being positive and this being negative. Well, if this is at 12 volts and there's nothing but a wire sitting here, and this is at 0 volts and there's nothing but a wire sitting here, well, guess how much voltage must be applied across this resistor? 12 volts, exactly. Hey, the good news is, if you know, remember, I is equal to V over R, let's just assume this is a 12 ohm resistor, right? 12 volts divided by 12 ohms, we would have 1 amp of current flowing inside this little circuit right here. Pretty simple math to figure out your current, your voltage drop, everything. This gets a little more complicated here, but same premise. If you have 12 volts here, and there's 12 volts potential sitting here, then assumedly the other end of this is at 0. That's how you get the 12 volts difference in potential. Well, guess what? That's a solid wire. So guess what potential is sitting across every one of these resistors in this circuit? There is 12 volts. So then if you knew the resistance value of each of these, you could simply do I is equal to V over R, and you would know how much current is flowing through every one of these resistors. But it's simple enough to know that 12 volts exist across this whole entire circuit, because we cannot remove nor create energy as in a circuit. Here, this gets interesting. It's a tough drawing, but there's a node here in the middle. In other words, there's 2 resistors, one on top of each other. Well, what you know here, if this is 12 volts, is that there's 12 volts sitting right here. You know potentially there's 0 volts sitting right here, right? 0 and 12, that's how a battery would work. 12 volts of potential across it. So you would know from here to here, if you put a meter, there would be 12 volts. But what you don't know is what's sitting right here in the middle, and that's what we're going to cover in the next section. I'll do the same thing again here. You could have 120 volts here, and guess what's sitting right here at this point and this point? The difference in potential between these two would be 120 volts, if that makes sense. Okay, let's move down here to the bottom where it gets a little more complicated here, okay? So here, if you had 12 volts, right, that does not imply you would have 12 volts sitting right here. And why is that? Because some amount would get dropped across this resistor as we would go forward. And whatever didn't get dropped by this, let's say 4 volts got used up and dropped across this resistor, that would leave 8 volts sitting right here. And there would be 8 volts here, and there would be 8 volts here. Why? Because they are in parallel. In parallel. And all this is one long wire. And if this was at 0 volts, guess what? This is at 0 volts. This is at 0 volts here. Okay. Similarly here, if we had 12 volts here, and we dropped, let's just say 8 volts here across this, we would have 4 volts sitting here and 4 volts sitting here. We would have 0 volts, 0 volts, 0 volts, but we still would not know what the voltage drop would be across this resistor or this resistor. We would just know that across both of them would be 4 ohms of resistance, or 4 volts of voltage drop, I'm sorry. This is where the fun begins. If you can grasp this, you got it made in the rest of electronics. I promise you. You use this all the time. It's the voltage divider. Voltage divider kind of principles here. And I promise you, I'm not going in enough depth here to make you an expert at it. So go watch lots of other YouTube videos and maybe find some practice courses online. And practice this stuff, but give you the concepts here. Let's say we have 12 volts here, right? And we have 4 ohms and 8 ohms of resistance here, right? And we're trying to figure out how much voltage is dropped across this resistor and this resistor here, right? Well, you can't just say V is equal to what? I times R. Well, we know R, right? But we don't know what V is across this resistor. So we got to come up with something else. We're going to have to find I if we want to solve for this. And we don't know the current right now. It hasn't been given to us. So we're going to have to calculate that. And the way we do that, if you'll remember, the current entering a node, let's call this node, is equal to the sum of the currents leaving the node, which means that what's entering here is the same as what's going through both of these resistors, making its way back around. So if that's the case, then all we got to do is figure out what's the total resistance here. Remember RT? Remember I showed you earlier you could draw equivalent circuits? This is nothing more than this circuit right here drawn like this, RT. So RT in this case, remember, R1 plus R2. In this case, 4 plus 8 equals 12 ohms. So RT here is 12 ohms of resistance. Now we know something we can calculate, right? If this is 12 volts and this is 12 ohms, what I is equal to V over R, right? 12 divided by 12 equals to 1 amp of current flowing through this circuit back here. Okay, now that we know 1 amp of current, what can we do? V equal to I, right, times R, right? So 1 amp, 1 times 4 equals to 4 volts. So we're going to drop 4 volts of voltage right here. And on this one, V is equal to I times R. We're actually going to drop 8 volts of voltage right here, which makes sense. Hey, back to KVL, the sum total around this circuit, right? 12 volts here. We're dropping 4 volts across this resistor, 8 volts across this resistor. 4 plus 8 equals 12. So we have not created or lost any energy in this circuit at that point in time. So we've just figured out how much voltage this thing is consuming and how much voltage this thing is consuming using a combination of Ohm's law, the ability to break down a circuit into its equivalent circuit, and calculating some values. If you were able to follow this, then you're pretty much set down the path of the math you would need to do for electronics. I highly encourage you to go watch some other YouTube videos where you do many of these equations and solve them and get better and better at it, would be my goal. Okay, we're on the home stretch here. Just 1 or 2 more sections here and we'll make it into some 2 amp schematics and see how this stuff actually applies. So this is pretty simple. If you have 12 volts here at the right here, well, guess what you have here, and 0 volts here, right? 0 and 12. Guess what you have here? You have 12. You have 12. Why? It's nothing more than a simple wire connecting them. They can't be at different potentials. The same here. 0 volts all the way across. 12 volts all the way across, right? Well, guess what? What's the law we know? I is equal to V over R, right? So if we're trying to calculate the current through each of these resistors, right, we just have to use this. If you already know the voltage drop across them, there's 12 volts being dropped here, 12 volts being dropped here. So really all that's left to calculate is I. If we know the voltage and we know the resistance, well, guess what? In this case, 12 over 6, right? 2 amps of current right here. And in this case, 12 over 4, there's 3 amps of current going here. And guess what? What did Kirchhoff's current law say? The currents entering a node must equal the currents leaving a node. Well, guess what? Leaving that node is 2 amps of current and 3 amps of current, right? Guess how much current must be entering the node? 5 amps of current. So the total current flowing through this whole circuit and making it back through is 5 amps. If you don't believe me, watch this. A much longer way of calculating this would be to figure out this circuit's what I call equivalent resistance, right? So we've got 12 volts here. And how much total resistance do we have here? RT. Well, RT, remember, equals to 1 over R1, which is 6, plus 1 over R2 here, which is 4, okay? And if we do the math on that, it's equal to 1 over 1 divided by 6 here is 0.166 plus 1 divided by 4 is 0.25 equals to 1 divided by, in this case, 0.416. And what that comes out and equals when you do the math on it, 2.4 ohms total, RT. Okay? So we could redraw this circuit just like this. Because that, if you're this battery and you're looking this direction from this imaginary line, then that's what you would see, would be this 2.4 ohm load of resistance. I is equal to V over R. 12 divided by 2.4, guess what? 5. So there's 5 amps of current total flowing through this circuit, which is what we calculated just a second ago. Okay, I just want to make really good ensure you get this voltage divider principle. If you remember, there's an imaginary node. This is the voltage divider principle. We use it a lot. Imaginary node right here. What do we know? We know there's 12 volts sitting right here. We know there is 0 volts sitting right here. We do not know what the voltage drop is across this, but how we would calculate that is we would have our battery, right? We would draw an equivalent resistance circuit where this is RT. If you remember, RT is equal to R1 plus R2 in a series circuit. So 2 here plus 4 is equal to 6, right? Then we know that I is equal to V over R. So we know 12 volts divided by 6 here, 12 over 6 equals to 2 amps of current flowing through this circuit, right? 2 amps. Well, then we know V is equal to I times R, right? So 2 amps times 2 ohms of resistance equals 4 volts being dropped across this resistor. And similarly, V is equal to I times R. 4 times 2 equals to 8 volts being dropped across this resistor. Well, hey, Kirchhoff's law applied again. 4 plus 8 here equals to 12, so we've not gained or lost any energy in this circuit. All right. So if you remember the schematic symbol right here that we used in the last video, is the schematic symbol for a variable resistor. It may also be drawn like this with an arrow through it, but more often than not, you actually see an arrow drawn straight into the resistor like that. And what it implies is basically the same thing as this, right? So if you had this, remember a potentiometer has 3 nodes to it, right? So if you measured the resistance between here and here, and this thing was, partially down right here, partially down this resistor, you may be sitting with 2 ohms of resistance up here, and if you measured from here, from this point to this point, you would measure 4 ohms. So 2 ohms here. And let's just say you slid this thing down just a little further, the wiper, you turn the knob, in other words, you might end up with 3 ohms of resistance on the top here and 3 ohms of resistance on the bottom here. And if you continue sliding this wiper down, or in many cases turning the knob, you might end up with, let's say, the opposite of that, 4 ohms up here and 2 ohms down here. If you kept sliding it, 5 ohms up here, 1 ohms down here. If you kept sliding it, you could slide it all the way to the point that you have 6 ohms on one side or 0 ohms on the other. And if you turn the knob completely the other direction, it would do just the opposite. In other words, this becomes a short basically, and then all the resistance is going through this side of the wiper. So that'll become important here, but the same voltage divider rule applies. If you've got this potentiometer knob turned to the point that there's 2 ohms of resistance at the top and 4 ohms of resistance at the bottom, and then this is really your node here in the middle, it's the same as measuring from here to here, would be the same as measuring here to here, right, across this point. Measuring here to here would be the same as measuring across here. The only difference between this potentiometer here and this circuit is fixed. We'll use this word a lot as we go forward. Fixed, as in fixed bias or fixed load. You can't really vary these. To vary this, you'd have to pull this resistor out and put a different one in. In this case, you can actually vary it, but as you vary it and make this one go up, this one goes down proportionately, and vice versa. I hope you grasp this concept because we're going to use it here in just a second. Okay. okay, a real life example here. This is a fixed bias cathode follower circuit with a triode vacuum tube here, probably a 12AX7, 12AU7, something along those lines. And what they're doing here, you just have to take a leap of faith with me right now and assume that everything to the left of this doesn't matter at this point, and kind of everything to the right of this right here doesn't matter at this point. But what we do know is that we have 200 volts sitting here, which means what? There's 200 volts sitting at this node. There's 200 volts sitting at this node. Guess what? That's good old ground sitting at 0 volts. So what do we know? There's 0 volts here, 0 volts here, 0 volts here, right? So if we know that you just have to take this leap of faith with me. For the most part, all the voltage gets dropped across here, right? And the current would flow through here, right? Well, then we could use the voltage divider law. And if you did the math on a 1 meg resistor and a 1 meg resistor, you add those two together, you get 2 meg of resistance. You divide 200 volts by 2 meg of resistance. You get the current, then you start multiplying the current times the resistance here. What you would find out is that across this resistor, 100 volts gets dropped and 100 volts gets dropped across this one, leaving, guess what? If there's 100 volts across this resistor, then that point is the same as that. So that leaves this node on this schematic right here at 100 volts. And that's what it says. So when the person was designing this circuit, they were very deliberate when they picked this resistor value and this resistor value, because what they were ultimately trying to do was create this 100 volts right here at this point. This is actually called biasing of this tube, and they intentionally picked these resistor values, used the voltage divider law to get to the point of voltage that they wanted right there at that spot. Let's move on to the next circuit. All right, let's make it real here. My goal in these videos is to basically teach you enough concepts to then apply to a circuit like this, so that you can start to understand the various components of the circuit. Hey, what does this thing do? What does this do? What does this do? You know, this looks like a fancy circuit over here. What does it do? I'm trying to teach you piece by piece what all these things do, so that when you look at a great big schematic, it's not daunting to you anymore. It's pretty simple. You can break it down piece by piece and figure out what each aspect of the circuit's doing. And if we add up enough of these concepts, sooner or later you'll understand the complete design of an amplifier and what it does. Well, today we're going to talk about this circuit right here and what it does, okay? And if you'll remember, this looks just like what we just talked about just a minute ago. This is a voltage divider here, right? This entire circuit right here, guess what it is? It is the volume control. So I don't care what device you go to, a guitar amplifier, your preamp, your stereo amplifier, your little iPhone, whatever, it's got a volume control knob on. And about 98, 99% of the time, this is exactly what makes up the volume circuit and exactly how it works. So let's just pretend for right now this device doesn't exist. I haven't taught you about those. So here's the way it works. Let's pretend that you've got a turntable, and coming off your turntable, you've kind of got this RCA jack, right? And it's got a middle conductor to it and an outer conductor. Let's just assume that the inner conductor is going to connect right here and the outer conductor is going to connect down here. And by the way, this is going to be ground. So, there's 0 volts of potential here, and whatever is being driven by your turntable, which by the way is about 5 millivolts typically, is making it right here to this input. Well, if the input's getting 5 millivolts, right, and let's just say this thing has an amplification factor of 1000, right, this tube that's giving you gain, well then you might end up with 5 volts coming on the output here, right? And so, hey, 5 volts, that's a little too loud in the room right now. Turn that down. Somebody's yelling at you. So how are you going to turn this amplifier down? Well, your turntable doesn't have a volume knob on it. So you're going to have to do something to vary the volume knob. And what you're going to do is you're going to grab the knob and you're going to turn it left, typically for down, and right for up. And when you're doing that, it's a potentiometer I showed you in the last class. And really all you're doing is sliding this little lever up or down, right? And if you remember what we just taught a minute ago, as you slide that thing up and down, what you're really doing is varying the amount of resistance on the top side of this and the bottom side of this. So think about current flowing in here, right? And it gets to right here. That's a node, right? Current has 2 options. One, it can go down here and flow back through and complete the circuit, right? Or 2, current can flow through here out the other side of the node. You just have to trust me on this one, but it kind of flows through the tube. Ultimately, in this case, it ends up coming on the output here and basically making its way back down and around. And it kind of goes out this way as well. But really all you need to know about this is that as current's coming into this node right here, right? If you crank this thing so that there's more resistance here and very little resistance on the top half, the current is more likely to flow into here and go this direction than this direction because you've created a lot of resistance. Remember what resistance was? The opposition to current flow. So as you crank that knob and you put a lot of resistance here, all of a sudden you start flowing more in here. And so you end up with a smaller voltage drop on this side, right? So you end up with more voltage, ultimately more current feeding into this thing, and less of it going straight back to ground, and, closing the loop on your circuit. So as you turn this knob the other way and you put very little resistance down on this end, and based on the resistance on the top side of this thing plus some of the other resistance on the other side of this circuit, we'll talk about more later, but you've given a really easy path to ground, which means very little of your current's actually going to make it into this amplifier. In other words, the amount of voltage being applied at this point because of this voltage divider rule here. Remember, we're kind of playing with whatever voltage is here, and we're kind of sliding it up and down as we turn this potentiometer, but you end up with less voltage right here on the input of this tube. And since tubes are voltage amplifying devices, if you have less voltage here, you will get less voltage out over here, which ultimately reduces your volume going to your speakers on this side. So I think you've just learned that, as this potentiometer here, if you'll notice, it's a 500K. Well, if you turn that thing so that you had 490K down on this end and only 10K of resistance on this side of it, that a whole lot more of the current would flow that way, ultimately putting a higher voltage potential here at this point, and not much would be making it down through this way. Hope that makes sense to you. It's just a basic voltage divider principle here, applying less voltage here or more voltage across this point here is what we're ultimately trying to do, and varying the volume into this amplifier. All right, the last little section of our video here. We have a Scott 222C power supply schematic. By the way, I'm busy making another video on a Scott 222C, an actual rebuild video, so maybe you can apply this as you watch the other video. So here's what you got. You got an AC power plug over here, right? AC power plug comes through a fuse. AC power plug feeds into a transformer. The other side of the transformer creates voltage. This voltage, AC voltage, you'll learn about that in the next video, I think, or one of the upcoming. This device here is a rectifier circuit, which basically converts AC to DC. And then what we have coming out the other side of this circuit is 430 volts at this node right here. And let's just, for all intents and purposes, this node right here is at ground. I kind of marked out the rest of this stuff at the bottom just to keep this circuit simple, and could teach you about the rest of it later. But so from here to here, we would have 430 volts of potential, right? So let's look at what we've got here. If you look at the total circuit, right, it would basically be here, down through here, down through here, down through here, and then kind of back to ground, whoops, all the way down through here, back around, all the way down through here, and back. And you could kind of consider this your battery at this point in time, your voltage source, right? So if you've got 430 volts sitting right here, and remember the whole voltage divider thing? Well, guess what? Here's a resistor, and a certain amount of voltage is going to get dropped across this resistor. Well, in this case, I haven't done the math, but 10 volts have been dropped. You know how I know that? Because they're telling me that right here at this node, there's 420 volts of DC voltage sitting here. Across this resistor must be 90 volts dropped. How do I know that? Because they're telling me at this point there's 330 volts of potential, and so 420 minus 330, there must have been 90 dropped across that. There had to have been 10 dropped across that. So then if we go from here to here, there must have been 30 volts dropped across that. Why? Because they're telling me that right here at this point there's now 300 volts on the circuit, and if there's 300 volts there, there's 300 volts down here, right? And then from this 300, there must have been 15 dropped right here. How do I know that? Because it's telling me that there's 285 volts sitting at this point right here, and then from here to here, they must have dropped 65 volts. How do I know that? Because there's 220 volts here, and the difference between that spot and this spot, the difference in potential between those, 65. So it's just plain old voltage divider rule here going across these things. You could add up all these resistances, the voltage, divide it by, create the equivalent RT, right? Add all those up, divide it out. You would actually find out then what the total resistance is. You could then, from the total resistance, do I is equal to V over R, 430 divided by this total amount of resistance would give you your current. You could then start multiplying that current times the resistance on each one of these to end up with what your V is. And in this case, it would have been 10 and 90 and 30 and 15 and 65, if all that makes sense to you. But just to show you, that's what, this is a practical application of a voltage divider circuit. And what they're doing with this, I'll show you here, is they're feeding different parts of the circuit that need different voltages. So this 420 volts right here, hang on one second. All right, I grabbed a little more of the schematic here, but right here's where we were, 420 volts, right? Or 430 volts, I'm sorry, and then 420 volts at this point, right? Well, that feeds up through here, right? Let's trace this all along. Oh, guess what? It's going to the center tap of the transformer, and you'll learn later. But then you end up with what? What does it say right here? 420 volts on the plates of both of these tubes right here in the output. So that's what they needed for the output tubes, right? Well, let's take another one here. Maybe this 350 volts right here, right? 300 volts that's sitting right here. It kind of feeds across here, kind of comes down to a point right here, and goes across this resistor, probably gets dropped a little more, and that's the voltage they needed for this tube. So each of these tubes, this is a 7199 tube. These right here are 7189 tubes. They operate at different voltages with different potentials, so they need different parameters set around them. And that's what we're doing here. We're getting the different voltages we need. Look, right here is 285 volts. Kind of feeds up here, right, to several different places. Comes across here, probably drops a little more across that, and feeds into the top of this tube. This is a 12AX7. It needs a different voltage on the plate than this 7189 does, which is different than this 7199. So they intentionally picked resistor values here in this power supply and used the voltage divider concept to basically provide different voltages to feed off to different points in this circuit needed by the specific tubes, because these tube manufacturers will specify the operating parameters around them, ultimately the voltages applied to the various components. They will specify things like the voltage right here on the grid of this, the voltage that needs to be applied on the plate. They'll tell you how much current can flow through this tube without causing damage. Ultimately, you change this resistor right here to control how much current flows through that. That's a cathode biased resistor. We'll talk more about that later. But you see how these basic principles of voltage dividers are used throughout these amplifiers to get different voltages at different places because of the requirements of the circuits that they're building upon. I hope you learned a little something today. If not, give me feedback. I'm just trying to make this stuff practical and real and teach you piece by piece, about a circuit and what all may be comprised of it, if that makes sense. Hopefully today you learned an immense amount about, kind of what does this thing right here do. Hey, by the way, if you'll notice, this is a balance control right here. Guess what it is? It's a voltage divider. So I can tell you right now, when that thing is dead center in the middle of that resistor, and there's 50k ohms of resistance on one side and 50k ohms on the other here, because it says it's 100k, well, right then and there, you have center of your stereo. In other words, equal amount playing left, equal amount playing right. As you slide this one way or the other, it would move more volume to the left or more volume to the right. If you just take each little piece inside of a circuit one by one and break it down, pretty soon it gets pretty simple. Down here, another balance control knob operates the same way. So, okay, real world video of what we've been talking about. Look, here's that schematic. There's the power supply we've been working with. This is what the amplifier actually looks like. I've got it on my bench right now. The negative post of my voltmeter here I've got connected over here to chassis ground, as you can see. The positive end I've got right here as a probe. I've got this amplifier turned on at this point in time, and it's kind of sitting up here. And I'm going to show you. So that first point coming off of that rectifier, if you'll remember, is actually this point right here coming off the rectifier. And if you'll notice, we have 410 volts. So the schematic said 430. We're actually getting 410. A lot of that has to do with the power being supplied by your line in your house. So mine might not be quite 120 volts coming in, causing me to have a little less here, but that's okay. It's okay. If you'll notice, there was a resistor that was in there to drop. Well, there's a set of resistors right here, and they're in parallel, and they actually are about 60 ohms total when you put them together. And if you'll notice, if I touch the other side of this thing, hey, I just went from 410 ohms down to 401 ohms. Well, if I come on the other side here of that resistor, there's another resistor here, and it drops it down here to this point. And if I touch that point, look at this. I'm down to 343 volts. Look here, there's another resistor. On the other side of that resistor, if I go touch it, I'm down to 302 volts. So as you can see, the way this power supply is working is it's coming off the main piece here with a higher voltage, 411, dropping down here to 401 at this point. Come to the other side of that, there's another resistor here. Get that, 343. Go to the other side of this little resistor right here, down to 303. And then from there, wires lead out of this and feed off into various places inside of this thing. In some cases here, the high voltage 400 and some volts ends up feeding the plates on these output tubes right here. Some of the 330 volts ends up going up here on the front end to some of the 7199 or 12AX7s that feed the front end of this amplifier. So it's the purpose. So what you saw on that schematic is kind of everything you're seeing here in this little section right now. That's what it looks like in real world. You know, this right here is what it looks like in the schematic, if that makes sense. So hopefully you learned a little something today, saw some real world practical use of how this stuff works. And then this right here is nothing more than a voltage divider network designed to provide different voltages to different places inside of this circuit, if that makes sense. Stay tuned, guys. We'll keep this series going. Hopefully you're learning something. Keep giving me feedback, and we'll kind of take it from there. Thanks again, everybody.